Okay, so today we're going to learn about vertical circular motion. Life's been really easy up until now. We've only gone around corners kind of on flat surfaces, or maybe we put the corner on a little bit of a bank to help us around, but we were always going around horizontal corners, horizontal circular motion. Today we're going to extend that to vertical circular motion, and there's a wee activity that you should probably go and do before this lesson that's going to help you, and that's grab a bucket, fill it with water, do that thing of swinging the bucket around and around your head. When you're doing it, I want you to try to feel what the forces are doing at each point. See what happens if you go faster and faster. See what happens if you go slower and slower. Is there a slowest speed you can go? Try that now. Okay, now I'm going to assume you've done it. We're going to go on and talk about what you felt. So, when the bucket was at the bottom, I'm hoping that you felt it was really heavy. And we can think about what's happening to the bucket at each point and try to understand why the bucket was really heavy at the bottom of the loop and maybe weightless at the top of the loop. Maybe if you got it going really slowly, and maybe you got really wet because you went too slowly and found that the water fell out. Let's try to work out what's going on. So, at each point, let's just have a bucket that's a red square. And so, thinking about the forces acting on our bucket, we know that always, no matter where it is, there's going to have to be gravity acting on the bucket. That's always going to be down. And we also know that the bucket's going around in a circle, and just at the moment, to keep things simple, we're going to assume that it's moving at relatively constant speed around the circle, that, you were giving it a bit of a heft on the way up to make it go faster, and you weren't letting it accelerate too much on the way down. It's not really correct, but we're just going to keep it simple at the moment. And so we know that for that bucket to move in circular motion, the net force on the bucket, like the total force on the bucket, has to be the centripetal force. There has to be somehow a center-seeking force that's going to cause that bucket to move at constant speed, but with a constantly changing direction. And so that centripetal force is always going to be directed towards the center of the circle. Let's have a go at drawing that on, see what happens. I'm going to draw it with a double arrow because that's our net force. Always towards the center of the circle. That's interesting, isn't it? And so, what else can be providing a force in this situation? Hopefully, if you went and did this first, you will have felt it. It's the tension force in your arm. That's the thing that's providing the other force in this situation. So, let's try drawing on that tension force in the arm. We might have to use black for that. And so, the arm is always going to be pulling towards the center of the circle. That's where it's connected onto, so it's going to be pulling in that direction. So down the bottom here, that arm is going to have to be pulling towards the center of the circle, and that's got to compensate for the weight of gravity. It's got to balance that weight of gravity, and it's got to provide the centripetal force. And so at the bottom of the circle, that F tension from the arm was really quite big because it had to provide both the weight force, it had to balance the weight force because there's no normal force, the bucket's not on the ground, it had to balance that weight force because at the bottom the bucket wasn't moving up and it wasn't moving down, it was just moving sideways. However, it was being accelerated up towards the center of the circle, and so that force, the centripetal force, also had to be provided. So the tension force at the bottom is the sum of the weight force and the centripetal force. At the top, check it out, gravity is helping us out a lot. Look, gravity is providing a large part of that centripetal force. The tension force just had to provide that little bit. And then on the sides, hopefully you can spot it, that we need our tension force has to balance the weight force, and it also has to provide the centripetal force. Are we good so far? So let's think about up here. This is where roller coaster designers really have to focus their thought, because things can go badly wrong, as you might have found out with the bucket of water. If the force of gravity becomes greater than the centripetal force, it's providing more force than what's required, then the water comes out of the bucket, or even worse, the roller coaster comes off the rails, going around the loop-de-loop. And so we have to make sure that for circular motion, we always have the centripetal force is greater than the gravity force. So for vertical circular motion, Fc is greater than or equal to Fg. So AC is greater than or equal to G. And that's going to be the condition that gives us the minimum speed for safely going around a loop. For the minimum safe speed. However, that's going to be complicated, as we're going to see in a moment, because if you're on a roller coaster, you start off up on a hill, and you start by going down, you're going really, really fast when you get to the bottom of the loop. But then as you climb up the other side, gravity does work on you, and you slow down, slow down, slow down. And so we need to make sure that we've got the roller coaster, or the bucket of water, going fast enough at the bottom to account for the fact that it slows down as it climbs up. We're going to use conservation of energy to solve that problem. Let's have a go and see what it might look like. That's you, designing your own roller coaster at home on lockdown. Don't want to stuff it up. And so you want to know just how high your ramp's got to be in order to make sure that you successfully pass around your loop, diameter 10 meters. And so we're going to start by working out just how fast is it that you have to be travelling at the top of the loop. And the minimum speed, remember, is the speed that gives us a centripetal acceleration equal to gravity. We can't have that centripetal acceleration any less than gravity. The minimum speed is when it's equal to gravity. So, let's give this a try. AC equals G. That means V squared over R is equal to G. V is equal to the square root of RG. V is equal to the square root of 5 times 9.81. Gonna get my calculator. Be back soon. Should have been able to do that without a calculator, shouldn't I? It's bang on 7. So that's the speed that we're going up the top of the loop. And so the tricky thing here is that we're going to get slower and slower and slower as the roller coaster goes from the bottom of the loop up to the top of the loop. And we can use conservation of energy to work out just how much slower it gets. And then we're going to use conservation of energy also to work back and find out just how high we need to make that loop. Conservation of energy, energy at the top must be the same as energy at the bottom. And down the bottom we've only got kinetic energy. Up the top we've got a little bit of gravitational potential energy and a little bit of kinetic energy. Nice thing about writing it out like this is you might have thought we needed to know the mass of the cart. We don't need to know the mass of the cart. Check out those M's. Boom, boom, boom. Just like that. Let's write it out again. GH plus half V top squared equals half V bottom squared. And we know almost all of those things, don't we? Let's start by multiplying by 2 to get that V bottom by itself. Hopefully you got 15.7 metres per second. Right, and then finally we're going to have a crack at working out just how fast how far the cart had to be up from the bottom of the loop in order to be going fast enough at the top of the loop not to fall off. And so I'm just going to leave those two results there and clear a bit of space. Now we can do conservation of energy analysis again and do this in several ways. One way would be to know that 15.7 metres per second is the speed at the bottom and just plug in to work out how much the gravitational potential energy is. And that's easy given where we're at the moment. I'm going to show you a slightly trickier way because it's going to let you skip even finding that speed at all. Look, that's how much the difference is between the height and the diameter. And so we're going to do a conservation of energy analysis of this again. And so we know that up the top here, the cart must have only gravitational potential energy. So energy at, let's call it E ramp. Is equal to mgh, and then when it's up the top of the loop there, it's going to have some gravitational potential energy and some kinetic energy. It's going to have squared. And notice I've stopped being lazy and I've put d for the height of the loop and h for the height of the ramp. And we've got to be careful. And we know that those two things have to be equal because energy is conserved. So we're going to start by cancelling those m's and rewriting it. And now we're just going to rearrange to find out how much that h must be. 12.5 metres. Cool.